If you tell me a truth that is yours that I don't care about and I don't know the evidence of, I probably will forget it. If you tell me a truth in a classroom setting and show me the evidence, I may remember for some time. But if you put me in a position where I discover that truth for myself in a space that matters to me, my life, and my future dreams, that truth is forever mine. When I think about my classes in linear algebra, one of the things that I want to do is position my students to learn linear algebra through a lens of their own dreams. In particular, allow them to study that theory by introducing them to ideas that they want to study in their future and contextualizing the entire curriculum through their own hopes and their own vision. This project is the second in a long series. I have at least 8 more in the queue, in which I'm trying to redesign the linear algebra class to have a choose your own adventure component. In any linear algebra class, I have something like 10 to 20 different majors. In my future, my dream, my desire, my vision is that every single one of those students will have a different experience contextualized in their major, even though underneath we hit all the theory. With that in mind, this particular talk is designed for a subset of engineers, which we'll get into in just a bit. I wanted to talk about an idea that is familiar with all of us, which is operator precedence, because I want to use this as a lens through which I think about this experience that I'm about to present. In our classes, usually not in calculus, the hope would be we don't have to worry about this, but we really have an idea of operator precedence, right? If I give an expression and say, please solve this, we all agree as a community, we kind of emphasize first highest order precedence is parentheses, we work down, we say PEMDAS. Some students have some confusion to recognize that M and D are on the same level from left to right, but blah, 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 blah. One of the things that's really interesting about teaching is that teaching is, this is what I would call either a simple or complicated problem, right? Like designing, solving an expression with arithmetic is simple. Creating a rocket is complicated. But the funny thing about complicated problems, this is from Nassim Taleb's Black Swan, complicated problems can be reduced into a series of simple problems, which can be solved over and over again, meaning to say that if you build a rocket once, you could probably do it again. Teaching is complex. In fact, it's way harder than building rockets. And we don't get paid as well, which is really frustrating. Just because I teach one student once doesn't mean I'm going to be able to recreate that for another student. And many of the things that allow us to turn complicated problems into simple problems are assuming difficulties away. But if I have a homeless student in front of me who is hungry, I cannot say to myself, I assume you're not homeless and that your belly's full, now let's learn. What I'm about to say I actually don't fully believe in the sense that I don't think that a complex problem like teaching can be reduced to an algorithm. However, if you put a slingshot to my head and you say to me, please determine for me a hierarchy of learning needs in an order in which you, Jeff, and your classes, you will address them, this is what I will produce for you. In a quarter system, that's exactly what we do. I get 12 weeks, I get 55 hours, right? So I have to choose on a day-to-day basis which things I'm going to prioritize. This model is how I think about this. When I think about P, the highest order, I think about belief and hope. And I particularly think about a Nas song, I know I can be what I want to be. If I can get my students to have this, that is the most important thing that I want to give them that quarter. It's also the hardest, right? After that, in my mind, the model that I have, and again, this is non-linear in reality, but if you forced me to sit down and write them out in order, this is the order. Next one would be motivation and goals. The kind of motto, if I was making a commercial, I know what I want to be and why I want to be that. So first, I believe in myself and I have hope for the future. Second, within that belief, I have a very strong context of where I want to go and why that's important to me and how that relates to my personal life. Third, after that, is what I like to call strategic deep learning. So not just learning, but deep learning, learning that is meaningful and lasts the rest of their life. And strategic because regardless of how theoretical I'd like to be, I recognize that we have to pay bills, time matters. So strategies to navigate that space, I think, are really important. So if I can get them to a space that they believe in themselves and they have hope for their future, if I can encourage them to create goals that are meaningful and articulate to themselves, if I can get them to think critically about how they learn, what skills they use, why, update, reflect, and change, then after all that stuff comes the COR. Right? Now, the sad thing is that although I like to think about this as the order in which I want to work, this is the easiest one to go to, right? Because that I have control over. I don't have control over the housing situation, I don't have control over food, I don't have control over finance, I don't have control over families, I don't have control over transportation. I definitely can, for myself, put together a list of content and think critically about what that content is, right? And so from the standpoint of reverse engineering a class, generally when I work, I try to go this way. One of the very sad things about that, though, is that I lose efficacy for a whole subset of my students. By the end of the quarter, people go away. And this makes me sad. It makes my heart cry, right? Because they're paying me. They're literally, every student that's in my class at census date pays for the food of my family and children, right? And when they go away, it means they've paid my bills, and yet I haven't served them in some way. In my early days, I used to think, what's wrong? What went on for that student that went wrong? And what I have learned is that that type of deficit thinking actually makes me less effective in my work. When I think about myself, the moment I think that way, I lose the capacity to change the systems in my classes to serve those students. The project that I'm about to present to you is a different paradigm in serving students, which is, instead of thinking when those students went away, what was wrong for them, I think, when those students went away, what did I do in my classes that did not address some of the fundamental needs in the higher orders? And what can I do to change my classes so that they stay, so that this resonates very deeply? The highest precedence I will not talk about here today. I have a ton to say about that. I also think that this is why great teachers stay in it. It's certainly not the paycheck, it's not the respect, but each of you probably have many experiences like this. When we touch students here, there's no amount of money that can give the feeling of that gratitude, right? Someday later, as I get all these things made, I'll talk a lot about how this relates to those. Today, I'm going to talk about this one in particular. And then I just have some words associated. Faith, why, how, what, right? So faith is most important, why is next, how is next, and then what do you do in that context? Highest precedence on top, lowest precedence on the bottom. So if I think about doing this, one of the first things I have to realize is the moment the state of California drops 40 students in my class, my goose is cooked, right? I have to create a situation where there's 40 different simultaneous experiences in the same room at the same time. And if I do that using traditional learning materials, there's one textbook, right? And that textbook is not really customized for the individual user, it's customized for the author, right? The author has only so many hours in their day, the publisher only has so many ways to print the book, so they're going to print the same thing that the author did 100,000 times. But my feeling is, well, you know what, we could do a lot better. Well, forget we, I can do a lot better. I can find ways to allow an experience to be customized to the individual user. But the first thing that I have to do beyond recognizing that this is a possibility, is ask myself, well, who are my individual users? Who are my people? What do they want? What are they searching for? So from that standpoint, every single, for the last 3 years, just like I do an intake survey in this talk, every single quarter I have a 4-page intake survey. It took me, with a bunch of different people, about 4 quarters to write that darn thing. And I've collected the declared majors. Now, I'm not claiming that declared major means motivation and goals. I'm claiming that that's what they write on paper, right? So there's a difference there. But these are the declared majors of 188 students in Math 2B, Applied Linear Algebra, at Foothill College over the last 4 times that I took it. This one makes me smile. This one in particular. She was awesome. Yeah. I'm going to outsource this for a moment. There's a lot to be said here, and I do think interdisciplinary is really, really powerful. But when I'm thinking about the biggest impact, I'm going to spend my energy where the most people sit, right? We can almost immediately see that here's a huge impact. And then from that, we can almost immediately see that okay, so now I'm thinking, okay, if I'm going to customize the learning experience for each of these people, where should I start? Now, many of you might think that what I think, which is I should start right here, except that the needs of computer scientists are a little bit outside the particular, what I would call base place. There's a barrier to entry for computer science students in linear algebra. To make that happen well, I think we need to actually change the entire structure. So I've prioritized stuff that fits within the current structure. 1 quarter introduction, no requirement for MATLAB, no requirement for numerical computing, right? Later in my career, you will hear me bark very loudly about how the current structure is really dumb. For now, I'll say, let's see if we can fit within the current structure to drive change. I started right there. So when I started thinking about this, including the eigenvalue project that I did a few years ago, I took the ones that were highest. Do you see that? So within that context, my immediate thought was, can I create what I call Roman keystone experiences? You're all familiar with the idea of a Roman arch, and there's that keystone in the middle. Every experience that I create, I want to be that center stone to an entire field. So for those of you that were at my eigenvalue talk, I don't know if you've, what was this whole thing that came out recently, the Nobel Prize in some sort of physics? I forget what this was. Terence Tao just, the Terence Tao just published that eigenvalue paper. Yeah, that field, the fundamentals of that field go back to the eigenvalue problem, and that's exactly why I chose that. The eigenvalue problem from that last talk sets a foundation for all of vibration analysis, and it shows up in 15 different fields. So if my students have that, it means that they have that introduction to every field, and that particular problem hits mechanical, civil, and physics, and applied math. Now that that project is maturing, and if you're wondering about that, I can field questions later in the question session. I moved on to the next one, which was electrical. What I want to do is create an entire theory and experience where all of my electrical engineers, physicists, applied mathematicians, and also engineers can make connections between what's happening in vibrations analysis and what happens at circuits. And I don't want those connections to be theoretical. In theory, practice and theory are the same, but in practice they're different. Einstein said that at one point, right? When I have my students in my classes, I want them to taste. I literally want them to be salivating, because all of the theory is in the field that they're interested in. So from that standpoint, this is kind of the model I use from this. My education, 100% of my math education was here. You ever walk into a linear algebra class and have someone give you an integer matrix? You know why those matrices were created? They're easy to work with by hand, and they're really easy to create. Do you know how long it takes me to create a linear systems problem with an integer matrix with integer solution? 3 minutes. I create a matrix, I create a vector u, then I multiply that matrix, I create the output, then I erase the vector u, done. So as an author of a textbook, if my goal is to create an entire textbook in a short amount of time, integer matrices are the easiest to make, right? Okay. But the moment that I do that, and I focus here, you know what I've lost? The imagination of my students. As if somehow they come into my classroom, and I tell them, hey, kid, someday you're going to need this. And they say, why? And I say, just believe me. You might walk into a Walmart and have someone throw an integer matrix at you. Or you might be walking down the street and you trip on an integer matrix. It's not going to happen, right? And students know this. They know it's all ridiculous. This is why I hear over and over again, why am I doing this again? I just got to get through finals and then I'm done, right? It's called a core dump right when finals are over, right? Like literally just erase that memory because everything I learned was useless. Right? Now I'm not claiming that all students feel this way, but I blame myself. When I put my students in a position that the only thing that they see is this, and they don't see connections between their lived experience and the stuff they're doing in my classes, that's on me. Now, I will admit, this is taking me, I think I gave my first talk on this in 2013. It took me 4 years of research that I do at night, weekends, and the summers. My wife has yet to leave me. God bless her. So when I say I blame myself, I don't really blame myself. We should get paid as much or more than every UC professor. We do a better job, we teach more students, and we do it as a fraction of the cost. If we as community college teachers got money to research, imagine this for a moment. You teach one class with 10 students, and all the rest of your time is spent developing curriculum. Yeah, that's how it should be. Right? Now, because it's not that way, and it's not going to be that way in a few minutes, let me forgive myself and say, I am given a textbook that has integer coefficients, and so that I don't die, I'm going to use that textbook as a learning resource. But in the project that I'm about to present, I refuse to do that. My classroom is my space, and I'm going to give the best experience that I have. One of the things that I want to do is I want to create real-world problems in the fields of interest that build technical proficiencies upon which students can excel in their future classes, and that give a gateway to the math that we work. In this problem, we're going to see this. We're going to create a problem that is immeasurable. The way I always talk about a real-world problem is, can you measure it? It's a really fast definition. It took me 4 years to come to, but a real-world problem is anything you can measure, right? And the measurements don't have to be a metric. Yeah, go ahead.
Just a quick comment on what you're saying about how we tend to focus on that right-hand side of your diagram. Since I am someone who's an electrical engineer, I mean, I don't want to put too much pressure on myself as a teacher to think that I have to build in all the components. I mean, in my junior and senior years as an electrical engineer, I've got the real-world part, and I had the tools that had been built, obviously through the ideal mathematical models, and then be able to apply. So,
can we save this? I have a lot to say about this particular subject. And let's immediately, I am not claiming, I'm not projecting my own neuroses onto you.
Sure.
Right? So I recognize fully how hard it is to teach, and
I mean, I am interested in being able to build in more components that have real world in it, but
yep.
Okay.
I have a lot to say about that subject, and it's a great, that problem is a real problem, right?
I'm loving this because I tend to do I call them the friendly numbers so they can learn the theory before they do the ugly, because they're all in physics.
Yep.
And I always say in a math class, if you get x equal 3, you know you did it right. In physics, if you get x equal 3, you know you did it right.
Yeah.
And I would point out, I said in math, we reverse engineer the numbers so you can get an answer and move on. In science, you're doing measurements. It's impossible to get integer solutions. We know, and I always say it jokingly. So I tend to, not dumb down, but I tend to concentrate on the
scaffold.
So I can get
scaffold. You scaffold it. Yeah. You scaffold it. Yeah. Well, these are great comments. I'm so happy to hear that this is resonating a little bit, right? So one of the things that I want to say is, in the space of linear algebra, I've seen tens of books. Gilbert Strang is the one that pulls out, Oliver and Shakibon, that introduce the idea of electric circuits as linear systems problems, but not a single book in the entire field has ever shown this useful for electrical engineering. It's in a way that an electrical engineer can study. And when I was looking at this way back in 2012, I thought to myself, I just don't have enough books on my shelf. Like if I just had the right book, somebody's done this. And what I realized in prepping for the last CMC Cube talk at Tahoe when I did this is it hadn't been done. Or at least if it had been done, it'd be kept proprietary software in like NSpice or Spice or something like that, right? So I then spent the last 4 years developing this, and then the moment that I developed the theory, I recognized not only did the theory not exist, but there's no easy way that students can actually measure this theory. Like one of the things that I always think about is democratizing modeling. Do you know another reason, aside from being overworked, underpaid, the constraints, the amount, in the last, I think PhD started somewhere in the 30s or the 40s, and the land grant thing that started the American institution started somewhere in the 30s and 40s, and if you look at the takeoff in the amount of university enrollment, that's about when it started, right? And if we look at the amount of science that has been produced since the time that bachelor's degree were introduced till now, it is exponential with a base lower than higher than 2, right? And yet, the size of the bag is the same. We still spend 4 years. Yeah. And you know what happens as the curriculum expands for the introductory classes? We just keep shoving stuff into that curriculum, right? And as we shove stuff into the curriculum, you know whose shoulders that goes on? Ours. We're the ones that have our name on that, right? When we certify somebody passes our class, we're saying, I have checked all the boxes in our curriculum. And I used to think that it was my fault that we were going so fast. Right? I used to think like, oh, I have to do this because of the COR, and what I've realized is we're really due for a reimagination. Like, and that's a different subject, that's a different talk completely, but like that pressure is real. The other pressure that's really interesting is that modeling is expensive. One of the reasons that we don't do good modeling in classes is because it takes so much money. Integer matrix takes 3 minutes of somebody's time. These things that you've seen are like $700 in 4 years, right? Like it's expensive. And so the thing that I want to do in my classes, and for anybody who's interested, is I want to make it cheap, easy, and accessible. If you want to do this, like every single one of these boxes is about 50 bucks. What you have in front of you, and you're welcome to open these, seriously, open them and, yep, go ahead.
So I noticed you've gone with manipulative based instead of looking for a simulator based way of doing that kind of thing. Is there a little philosophy?
Yeah, we'll get into this. What I'd love you to see is, go ahead and take these out. We'll go ahead and switch over. So you can kind of play if you've never seen a breadboard before. We'll go through each of the different components that we have here. All right, so what I'm hoping is that each of you could have a few things in front of you. This thing right here is called a solderless breadboard. It's a 400 point. On Amazon, I got 6 for $10. I think you can get them cheaper if you do Alibaba and you don't care about when the due date comes, right? These right here are called resistors. Resistance is futile. That's cute. Ohm's law, some of you may be familiar with Ohm's law. These are the actual physical components that allow that to happen. These have never existed. Well, if they have existed, I've never seen them. These are hand-built, designed for this experience. I've never seen an actual physical current source. This is a DC current source that provides 2.5 milliamps of current over many, many loads. And it plugs into a 9-volt battery. This thing is about $3 and something cents. We'll be doing that in a second. So this was designed for this project by an electrical engineer and 2 of my students, PCB. They designed the PCB board and they printed it out. And this is also a 5-volt voltage source that connects to a 2.5 volt, a 9-volt battery. So from the black to the red provides a 5-volt. What I'd love to do, if you take a look at the example handouts, and I'll steal one from over here. I'd love to show you some of how I imagine this works. So this is an introductory circuit that we would see in a classic circuit analysis class. This thing right here is a voltage source. Could you guess which component corresponds to that, the physical components? Yeah, do you know what's crazy? I have a picture in a second. These were finished on Thursday. And the students that finished them, I didn't ask them for stickers. They thought about that for themselves. So when I saw them, I actually got down on the cement and bowed. That was very creative. Okay, so that one goes there. Down here, you'll see a bunch of parts that you need. So this thing right there is called a circuit schematic. You'd see this in a standard textbook. These are the list of parts that we need. And if we turn on the back of that, here's how we build it. And I actually want to do this with you if I'm allowed. I'd love to actually like take some resistors out and get dirty. At the end, I might ask you to help me get everything back into the bags, just because there's one of two of me and my team. There's not a lot of hands, right? So please do get your hands dirty. Let's go ahead and spend maybe 5 to 7 minutes trying to create this circuit. I didn't have 40 hours to Photoshop this thing into that software. So could you guess what this one is, the 5 volts? Yeah. So see if you can follow these instructions. Insert resistor R1 across B10 and I10. Let's see if we can find that, and then we'll shut up. Yeah, go play with it. Go play with it. I'm going to shut up for a bit and let you play. Yeah, me neither.
All new.
That's cool.
I'm like, you look at
These are not expensive enough that if they break, I'm going to cry. In fact, if you break them, I might treat you to a glass of coffee, because that means you were really trying to test the limit of the stuff that we created, right?
How deep do we push them into the hole?
Until they stop moving.
No, I can't. I have 5 thumbs. Little assistant drivers.
I'll show in just a second. We're going to do some work together. It looks like some folks are ready. Okay. If you finish, there's still some folks working on it. What I'd love you to do is flip through that sample of circuits. Like there's 4 of them in there, and I hope you'll see that things get much more interesting very quickly. There's some tears I'm going to share with you in just a minute. And then once you flip through that packet, go ahead and take a look at the 28-page packet, the other one, and just start flipping through it. You don't have to read anything. You don't have to understand it right now. Those are yours to take home if you'd like them. I have not yet submitted this for publication. This is fresh off the press. I always like to do something special for CM3 Cubed. I love community college teachers. You all change the world. I'm a community college teacher. We change the world. So this is a gift from, you're welcome to recycle it, or you can give it back too. I'll go to my next presentation with them. Okay, it looks like most of us are working through. Okay, so I want to do something really quickly. What I'd like to do is, I don't have 9-volt batteries for all of you, but I wanted to show you that that's a very low barrier to entry, right? You don't have to learn how to use a bench power supply. You don't have to learn how not to shock yourself. In fact, like I can connect this. So here we go. Yeah. I'm safe. No death, no fire, right? That's a great question. I'm so happy that you asked that, and I don't know. The gentleman that helped me design this worked in optic laser surgery, and I'm 100% certain that he would have access to people that could answer that question, right? I'm what I call an idiot that tries to look smart from this standpoint, right? I've taken one electrical engineering class in my life and 0 physics classes. So everything that I learned was from a book, which makes it really fun for electrical engineers to talk to me because I don't know how to pronounce anything. Telegin's theorem, telegin. Yeah, Thevenin and Norton as well. Okay, so what I want you to do, what we're going to do together, let's go ahead and make a bijection between these variables, u1, u2, u3, and u4, and the corresponding spaces. Could you guess where u1 is, this variable u1? Could you guess where that is?
Further right lead is.
It's like right there, right? Okay. How about u2?
Right there.
It's like here, right? Yeah, kind of nice. That took me many, many months of thought about how to design that well. How about down here, u3 and u4? So now what I want you to do, if you can, get out a pen, and we're going to go ahead and track some variables. So I'm going to hit the black lead down here. So black lead is on u4. Red lead we're going to attach to u1. And we're going to say that the value of this thing via measurement is 4.96. Okay. So could you write down u1? You could write it. Oh, that's awesome. Courtney, can I pay you in cash, credit, or check for that? Can I show? Yeah. Courtney, look at what she did there. You stole my heart.
Oh.
Yeah. Okay, should we do the next one?
So this is the resistance then?
We'll talk about the value of this in just a second. This is actually the voltage potential across those nodes. So you can think about this as a height measurement. So from the baseline down here to up there, you can think about like as 4.96 feet. So if you drop something from 4.96 feet, would it go faster or slower than if you dropped it from 2 feet? There's more energy at 4.96 feet, right? There's no more potential to create flow. Okay, let's do the next one. Let's do U2. Okay. What is that, 3.314? I wonder if the circuit gods wanted to do something like pi for us. All right, should we try the next one? 1.657. 1.657. I feel like I'm at a lottery game. And then 0.1 millivolts. So that's, oh, there we go. Whew. I felt the pressure there for a minute. Okay, you got him, right? All right. So I'm not going to steal the fun stuff for you. There's 22 pages of written math that I am 100% confident every single one of you could figure out. What I am going to do is present an idea, which is that problem, oh, these are the two guys that did it. This is Chris and Hayden. They showed up Thursday afternoon with these things done. This is epoxy. What I really want to do is get these things to cost like $1 each, so that anybody that has like 20 bucks can have a functional lab, right? The point is to democratize modeling. So voltage source, current source. Here's the thing we've just looked at. Okay, so we built it. That matrix encodes that problem. And in fact, so you can write that down for yourself. And do pay attention here. The subscript is quite important there. My electrical, I'm so, any other?
I was going to say that's an idealized version of what we...
Yeah.
That's really in it. Those are integers.
Yeah. So you know what happens, right? Yep. Yeah, we'll get there in a second. You're like 3 steps ahead of your teacher, 4 steps ahead of the class. I always tell my students that even though they want me to stop singing Aladdin, I never will.
That's why they drop.
Yeah, I can't help it.
I know my students would if I sang.
Yep. Okay, we got it? All right, now we get to make some money. Because we have something intelligent to say about this. If you'd like to, you can apply, what's the inverse, the 2x2 inverse formula called? I forget at the moment. Kramer's rule, Kramer's formula. Yeah, so if you do, I forgot, there must be a pen in here somewhere, right? So there's this really famous formula that you can derive quite quickly, that we can derive quite quickly, that I think it's like this. If I have, let's see, 2, -1, -1, 2, Oh yeah, sorry. A little technical difficulty. I think this was U2 and U3. I did this at like 3 a.m. this morning. I gave 3 finals this week and I graded them all, and so I couldn't start doing this last bit.
I'll send you a couple of mine this week.
Okay, so I think there's this, I think it's like this. It's been a while since I thought about this, a few days at least. If I swap these two and then make these positive, and then I take the determinant of this thing, so the determinant is 2 times 2, 4 minus 1. That is now the inverse of this matrix. Yeah, so if I apply that inverse to this thing, I should get the output. But you know, I always tell my students that there's a reason why TI gets a lot of money, and that reason is that when I'm tired, I shouldn't do math, and in general, I should never do math in public, right? The actual arithmetic. I do it at home, and then when I show up in public, I tell people I'm doing it off the top of my head, right? Because that's what all my teachers did. Okay, so that's that matrix. Did you see that? I just typed in that matrix. Let's go ahead and go into the vector. Sorry, sugar. Oh yeah. Watch this. So let's do this one. We'll edit it. Okay, so now we go matrix A inverse, which is a stupid numerical calculation, but that's okay. I forgive myself. Okay, so what was the value, the theoretical value of U2? Okay, compare it, write in a different color, put it right next to U2 up there. What was the numerical value of U3? Okay. And we had a very astute observer who said, hey, Jeff, you actually did a theoretical vector B because you said that the voltage potential of this thing is 5 volts, but the measured voltage potential was not 5 volts. What was U1? What was the value at U1? Okay, so why don't we go ahead and say, you know, and this is part of the modeling process for students, right? They get to discover that for themselves, and I don't have to say, how would you make it more accurate? They get to ask that question, and that's where we enter it. Which means it's not me telling them that, it's them discovering that, right? And they might say to themselves, well, how would I make it more? It takes a little bit of time, but let's go back down into this thing. And let's turn this one into 4.96. Okay, so now let's go back to the basics. Check that out. And why don't we do 2 digits of accuracy so that this talk can seem more legit. How's the measurement line up with the model? 10 to the negative 3, right? I have a physicist friend who said, if you get stuff within 10 to the negative 3, go home and eat dinner. Which means my students don't need me to provide them an answer key. Because the problem's not over if I design these well until the model and the measured line up. So, pretty cool. Let me switch over and let me show you some other results. So, we haven't talked about, there's a whole theory about once you have the 2 variables here, how do you then calculate this one? This is what we call ground node. It's always 0. When a ground node is connected to any node via a voltage source, the node that the ground node is connected to is called a non-essential node. So in particular, U1 was 4.94 when I did it at 3 a.m. this morning, right? So here, some of you got 4.96, right? And then claim we can use these 2 to actually, and information about the topology of the circuit to do this. So the thing I wanted to show you next is this is a much more interesting circuit. I have there's a part of my heart that is crying right now and desiring quitapenas, un trago de quitapenas, which we'll talk about in a second. There's the circuit actually realized. There's the matrix.
Now, how are we getting this matrix?
I've spent the last 4 years coming up with an algorithm to turn nodal analysis into linear algebra.
I was going to make one more comment on that very first example. I'm sure that if you make that a more accurate value for the resistance, you can even model it better
Yep.
in those idealized values you want to take resistors.
So you know what's really interesting about that, right? That we start to get into cost. Students can see costs, like the amount of money that it takes to actually spend, forget money, that's time, right? Somebody has to do that. And so the question is it worth it? And if we analyze, so what they're saying is that each of those resistors has precision. So right now we're saying they're 1 kilo ohm, but they could really be like 998 kilo ohms, right? So if you were to update these things, you get a much more accurate count. But at some level, the question is, do you want to measure 45 resistors with an ohm meter? Or should we idealize it? And what's the benefit of idealizing it? What would idealizing mean? One of the things that I saw in the electrical engineering standpoint is all this stuff having to do with Kirchhoff's voltage laws, Kirchhoff's current laws, all of that is in scalars. It's all in scalars. So the entire nodal analysis you have to do by hand. That's really nice if you give me a circuit like this. Do you know what happens if I give a circuit like this to an engineer and say find every node potential? They go away for a few days, right? Claim. The algorithm, this has never been published that I know of. That algorithm is called I like to call it LANA, L-A-N-A, linear algebraic nodal analysis. It actually contextualizes all of nodal analysis through the lens of linear algebra. It also completes, has anybody ever seen those circuits in linear algebra books? This puts a wrap on this. This algorithm that is in this, that I've presented to you, makes this useful for engineers. It's no longer a toy. Every single circuit that I've seen in every math book that I've ever looked at, they're all toys. They're useless. Because all of the assumptions that they make don't actually correspond with the type of circuits that engineers work with. And that's why I did this project, because I thought to myself, there's a whole subset of engineers that are in these classes having to take this stuff because it's useful. But the way that they learn the math is not the way that they see the math in their classes, right?
So you could pair this with like strings.
I actually showed in Strang's Introduction to Applied Mathematics. That book was the one that I used, and then Olver and Shakibon built on that, and I closed the loop. Strang does some stuff in that electrical engineers would look at and say, what are you on?
Yeah.
Right? Because he doesn't close the loop. He does it in general and says, oh yeah, you can do this, but he actually doesn't show it. This closes that loop.
I was wondering if he just like had a conversation with someone and just said like,
Let me put that in, right?
Yeah.
So this is a gift.
Is it, going back to the original matrix, the 2, -1, is there anything you can point to on that circuit that can explain what those 2 vectors are?
You're asking this is what we call stiffness matrix, and you're asking, can I get a sense of what the 2 and the -1 and the -1 and the 2? Mm-hmm. Yeah. I haven't actually done this formally. Let's see. So your question is actually about graph theory. There's a whole in this circuit, there's actually 3 different things happening. There's topology, there's what you might call properties of materials, and then there is the network dynamics. So right here, if the current is going in and the current is going out, those 2 things, that 2 says at that node, you've got the influence on these 2 resistors, right? The negatives have to do with, I don't have this in a presentation form right now. In the back of this, I'm 100% serious about this. Me and my team have been working hard on this, and if you feel you're interested in this, I would love to serve you. The amount of energy that is taken to get this in this form is really, really high. The question that you're asking, I have answers to in my deep work logs in the morning, but I have not prepared to speak about it in public.
Fair enough.
Crazy thing is, there is a proof to show that as long as this is a real circuit that cannot be divided into subcircuits, those things will always be non-singular. Which is really fun. So this is always a non-singular matrix. It's actually positive definite. And it shows up as A transpose CA, which is really, really famous in tons of fields. Remember I was talking about Roman keystones? The reason that I started here is because this is a physical realization of something that shows up in like tens of fields of mathematics. And people quote that this has been done, but they don't actually show it's how it's been done. And so when I'm thinking about that Roman keystone, I want to hit the spaces that make those connections real for students. And so when they get it here, they'll be able to base their next class on a hard, experiential set of experiences that they had in their classes, right? Yeah.
Is it always a metric?
Yep. Because it's in the form A transpose C. Do you remember the normal equations?
Yes.
A transpose A? That's because it's a non-weighted inner product. The C, the matrix in between here, let me slow down here. I don't like to get too technical, but do you see what's happening just in this experience? I heard people sharing, instead of me talking when you were building this, people were talking together, right? In fact, I heard some people teaching other people. And then the moment that you're here, you start coming up with questions, right? That's not driven by me. That's the really powerful thing about this. Instead of me having to drive the conversation about the mathematical analysis, the students get to work backwards into the mathematical analysis, realize that it's not perfect, and then start asking questions about it. This gets into the question session, which is, how do you have enough time to do this? And we don't, right? I'll stop here because I want to give you a chance to ask questions, and I'm really hoping you'll fill those surveys out. I have a ton to say about that matrix structure. This document, this large one that feels like a weightlifting set, introduces all 14 steps of the linear algebraic nodal analysis algorithm. It's the first time it's ever been public other than my small team. It's not published yet, so I would appreciate it if none of you swoop me, right? I have enough evidence to show that this is my intellectual property, so I'm not so worried about that. And then the funny thing is, right now, I actually have a challenge for every one of you. I don't know how to redesign my classes to use this. This is a Ferrari. It's built now. I don't know how to bring this into the classroom. The way that I have been doing this is through independent studies. So I've done now 3 separate independent studies where students do this for themselves. And that's been a really nice way for me to get a sense of what students' needs are and to get a sense of how this whole thing works. If this is interesting to you, you know what I'd really love to do? I would love to give, if you want it today, I'd love to have you take those home, except that I'm $700 in the hole right now. When I go to bed at night, I want to wake up next to my wife for the rest of my life. If I gave all of those away, I might put that in jeopardy. However, I'm not looking to make a profit. If this is something that you're interested in, I could sell them at cost. Not because I want your money, but because I need to look my wife in the face and say where that money went, right? And then if that's the case, if you're interested in this, I offer myself and my whole team to you to help you think about how this whole thing works, if there's problems with all of this stuff. But the real question that I have is, now that this is built, what do we do with it? So, yeah. I'm open to your questions. And I think you had some, but I don't know. Maybe we'll start with them and go this way. You had this beautiful question about the comment earlier, right?
You talked about the one where I was talking about changing the matrix on the left.
At the start of the talk, you were saying I don't want to put pressure on myself to.
Oh yeah. In
Yeah.
terms of whether or not to, how much as an instructor do I really want to go ahead and allocate in my teaching? To be trying to incorporate some of these. I mean, they're great. I'm not denigrating them, but just realizing that it takes so much time just to go through the theoretical aspect of what we have on that right-hand side of the first slide that we had. Try and build in something like this and weave it in. And then, as someone who went through an electrical engineering program, I was shown in my electrical engineering classes how the math actually worked for doing analysis. And then we got the breadboard and all that stuff.
So I'm going to repeat this out loud so you can all hear it. The concern that he has is the same. That's the rubber band to the head, right? I get 55 hours face to face, and I have to use those 55 hours well. So I bow to Salman Khan. I cannot believe that I was the first person to register the domain name appliedlinearalgebra.com. I cannot believe that my senior colleagues did not think to themselves, I should grab that name. So this is my website. I pay $180 a year through Squarespace. It's an education account. Not bad. I want to show you, I do this in my moonlight hours. If you go to blog, in this case, why don't we do students first and then we'll do teachers. So 4 students. This is me. This is my linear algebra class. 2 years ago, a man named Chuck from Kenyatta College, I'm writing a textbook. I don't know if I'm going to publish it for money. That's going to be something that the publishers have to be very, very convincing to me. There are some really good things about open source, and there's some good things about publishing in terms of support. The man Chuck in my talk said, you should put all of your textbook online so we can use it if we want. So after that talk, I put it all online. It's right here. There's 367 pages of this manuscript. You can click on this thing. This is something like 600 hours of work available for you for free. And then students said you should make videos. So I did. This is my YouTube channel. If you give me your email and you want access to this, all you have to do is say yes, follow up. This is the first talk about that particular modeling thing. I actually run through the entire applied linear algebra. This quarter is the first quarter where I did not lecture, well, I lectured twice, sorry. It's a flipped classroom model. You're welcome to use these. If you use them, I would love to know that you're using them so that I can know every time somebody gives me what I would call a gift, which is constructive criticism, I listen carefully and I change. So if I know you're using them, then I can be aware of your constructive criticism, and then as I do my next iteration, I can change those things. This solves the problem of how do I deal with the in-class stuff, right? It doesn't solve the problem as how do I get this. There's a bunch of other stuff on top of this, but I didn't lecture a single day in my class this quarter until last week because I hadn't finished those videos yet. Right? It's all available for you. So I guess what I should do now is shut up. I wanted to show you something so you can take a picture of it. If you fill out that survey and you wanted me to contact you, I'll do so. And I will give you links. I hope to do it a little bit better this year. I'll give you links to everything that I'm talking about here. This is my website. You saw how to go blog for students. If you went for teachers, there's all of this stuff is posted online. My YouTube channel is the same exact thing with capitals. I am not good with emails, but I'm great by phone. Thank you so much for your attention today.